Hello students, today we will be seeing the topic moment about the mean. In the last video we had seen moment about the origin and what is a moment and what are the different types of moment. And this moment about the mean is also called as central moment. Yes. So let us consider a real function g of x. Of a random variable x such that now here we will be defining the function g of x. Here g of x is nothing but x minus x bar raised to n because we are taking moment about the mean. Here n is equal to 0, 1, 2, 3, right? So the same thing. Next, we will be defining for the continuous, that is central moment for the continuous random variable. And the central moment or the moment about the mean is represented by mu n. And for the continuous random variable, mu n will be nothing but expectation of x minus x bar raised to n. So this can be written as, just apply the formula of expectation, it will be minus infinity to infinity x minus x bar raised to n into fx of x, which is density function. In this way we will be writing the mu n, that is moment about the mean value for the continuous random variable. Next, we will see same thing for the discrete random variable. So discrete random variable, just I'll be taking the again mu n. This will be equal to expectation of x minus x bar raised to n. This will be equal to, we have to apply here the expectation formula for the discrete random variable. Summation I is equal to 1 to n, all the values of xi minus x bar raised to n, probability of, this will be multiplied with probability of xi. So in this way we will be defining the discrete for the discrete random variable central moment or the moment about the mean value. Now just recall what is the definition of the moment and what is the definition, different types of moment, and also what is moment about mean. And what is moment about mean also called as, one more name of moment about mean, and what is the formula for mu n for a continuous random variable and mu n or the moment about the mean for the discrete random variable. So all these things, just think. Yes. So moment is nothing but it is the set of statistical parameters to measure a distribution. Types of moment, there are two types of moment, moment about the mean and moment about the origin. Moment about the mean is nothing but when we take a function x minus x bar raised to n, and when we calculate the moment, then it will be called as moment about the mean value. When we are calculating moment about the mean value, we are calling it as moment about the mean. And moment for the continuous random variable, we will be taking that is expectation of x minus x bar raised to n, and integration of that value into density function. In the same way, for the discrete random variable, we will be taking x minus, that is summation of x minus xi minus x raised to n into probability of xi. So in this way we will be defining all these values. Next, uh, just we will take one more thing, that is whatever values we have now, that is central moment value, we will calculate by putting different values of n. So first, yes, one second, yeah. First, I'll be just putting n is equal to 0. So when I put n is equal to 0, I'm going to get the 0th central moment. 0th central moment. So this is nothing but mu 0. What is the formula? Expectation of x minus x bar raised to n. Here if I put 0, what it will be? N is equal to 0, x minus x bar raised to 0. So expectation of something raised to 0 is 1. It is nothing but 1. Hence I can say that 0th central moment. 0th central moment is equal to 1. Also you can elaborate this by writing the formula, that is integration of minus infinity to infinity x minus x bar raised to n fx of x into dx. Now I'll put n is equal to 0 here. So this raised to 0 fx of x into dx. I'll be left out with only minus infinity to infinity fx of x into dx. So complete density function value from minus infinity to infinity, just it will be equal to 1. So I can say 0th central moment is nothing but it is equal to 1. In the same way, if I put n is equal to 1, put n is equal to 1 in the, then I'll be getting the first central moment. First central moment. So same I'll be putting in the formula of mu1. mu1 is equal to expectation of x minus x bar raised to 1. So this will be, again apply the formula for the expectation, minus infinity to infinity x minus x bar raised to n into fx of x into dx. So mu1 is equal to, it is nothing but expectation of x minus x bar is equal to, can I split this, that is minus infinity to infinity x, because it is n is equal to 1 here. So I can write it as x into fx of x into dx minus one more value, that is minus infinity to infinity x bar into fx of x into dx. What is this actually? It is the mean value, that is expectation of x. It is the mean value formula. So I'll be writing that, that is x bar minus this. Again I can take it as x bar is a constant value, so it will be minus infinity to infinity fx of x into dx. We know that total density function will be equal to 1. So just it will be equal to x bar minus x bar into 1. So x bar, so it will be just equal to 0. That is nothing but first central moment value is equal to 0, right? So in the same manner we will be calculating for uh, n is equal to 2. So I'll put n is equal to 2. Then I'll be getting the second central moment. Second central moment. And this second central moment is very important quantity. It is also called as very important concept. It is also called as variance. The second central moment is called as variance. Next, so if I put it like mu2, it will be just equal to expectation in the formula x minus x bar raised to 2. So apply the formula of expectation, minus infinity to infinity x minus x bar square into fx of x into dx. So now just expand this by applying a minus b whole square formula. So it will be what? Minus infinity to infinity x square fx of x into dx. I'm expanding and writing the terms separately. So plus b square, that is minus infinity to infinity x bar square into fx of x into dx. Also this minus 2 into minus infinity to infinity 2ab, I'm multiplying fx of x into dx. So if I so this is nothing but, see here, x square into fx of x into dx. So it is the mean uh, moment about the origin square, that is mean square value. So I can just write this as x square bar. Again, when you expand, when you simplify this, this is nothing but x bar is a constant. See here, just I'll simplify. So this this I can write it as just x bar square into fx of x into dx. So I'll just take it as x bar square, because the other term, this is a constant term, and minus infinity to infinity fx of dx will be equal to 1. So here what we can take is 2 x bar into one more term that is remaining, that is x into fx of, that is also mean term. So I can take it as x bar. So it will be what? X square bar plus x bar square minus 2x bar square. So this I can write it as x bar square minus this and this. So it will be x bar square. So this can be written as, so what is this actually? This is nothing but expectation of x square minus, here it is what? Expectation of x, this whole square. Just once again I'll write it here. The last what we have got is and this mu2, that is variance, can also be written as sigma x square is equal to mu2. Mu2 is nothing but what we have got, expectation of x square minus expectation of x, this whole square. So this is nothing but expectation of x square, means I can write it as moment about the second moment about the origin minus first moment about the origin square, right? M2 minus M1 square. So finally I can write it as mu2. One way of writing is M2 minus M1 square. The another way is x square bar minus x bar square. So this way also we can represent the variance. Yes. So this is about the moment about the mean value, and by putting different values of n is equal to 0, n is equal to 1, n is equal to 2, we have got different values of moment about the mean value. So we can also say, I mean, like, yeah, one more thing, like we can put n is equal to 3 and we can check what will be the expression. So yeah, that's it for this video. We will again meet in the next class, next video, by taking the properties of the variance. Thank you.